Hello, and welcome to Physics for Play. In this episode, we're going to be looking at the physics of the damped and driven harmonic oscillator, where you have some frictional forces. Your oscillator is also being pushed by an external force. Let's get started. Last time, we talked a bit about forced harmonic motion and resonance, and we gave the analogy that it's kind of like pushing a kid on a swing. And we solved the differential equation for the forced and undamped case. So the case where you're pushing on the swing, but you do not have any damping or frictional forces. And in that instance, we saw a solution that if you push at a certain frequency, so that the frequency that you're pushing at matches that resonant frequency, which is the natural frequency of that you're driving at, then you get this huge amplitude. You get this infinite amplitude that blows up, and obviously you're never going to have an infinite amplitude in the real world. And the reason is the real world has friction that slows you down before you can have anything that approaches infinity too closely. So today we're going to talk about adding that damping force, that frictional force in. So we're going to begin, much like the undamped case, we're just going to start with our equation of motion. But this time we are going to add a third force in here. That's going to be the linear damping force. So we have minus kx, the Hooke's law restoring force caused by the swing or the spring. We have the force that we are pushing with, that driving force that goes as F naught cosine omega t. And now we have a frictional force that depends on the velocity. So it's going to be minus a constant times that velocity x prime. So as always, we are going to try to solve our differential equation by guessing the solution. And since it's we anticipate it's going to be an oscillatory function, we're going to use our usual complex exponential guess for that. So we're going to guess that the solution is x of t is equal to some amplitude times e to the I omega t minus delta, where omega is the same angular frequency that appears in the forcing function, the driving frequency, because we are guessing that our motion is going to match what that driving frequency is. So we're going to go ahead, we're going to copy this equation, and we're going to try to find the solution for this differential equation. Now, you'll note that I've referred to this section as solution number 1, the particular solution. The solution we're going to try to find right now is known as the particular solution. It is not the only solution, but we'll cover the complementary solution in another video. But for now, we're just going to focus on this. And like I did in the damping video, I'm actually going to rewrite this. Since we're using complex exponentials, we're going to say that rather than a cosine here, we're going to just write it as the real part of a complex exponential, e to the I omega t. A couple other things which will make our lives easier momentarily is I'm going to define two constants. I'm going to define I'm going to define the spring constant k in the usual way. It's going to be m times the mass, m times the angular frequency squared, or the natural frequency, I should say. And I'm going to define b, the damping coefficient, as in the usual way. That's going to be m times gamma. And when I plug this into the differential equation, you can see I get a nasty algebraic equation. Lots of e to the I omega t's and other stuff that, fortunately enough, we can simplify. We're going to use Mathematica to do the hard work for us. And you see we've got an equation that looks a little bit similar to something we've seen before. when we've plugged in our ansatzes. You've got a part that depends on time, and you've got a part that does not depend on time. And we know that if the solution is going to be true for any time I want to plug in, well, I can't worry about picking constants over here because the time is going to change the value. So I can't pick a particular set of variables that will set that equal to 0. But if I set this half equal to 0, then the whole thing will be 0, and this will always be true. So we are going to look for the solution where everything in parentheses is equal to 0. So I'm going to copy this down. And you will note that everything in here is not just a algebraic equation, but it's complex. So there are real and imaginary parts. So I am going to break these into the real and imaginary parts. We're going to do RE to get the real part. And I'm going to copy this and write down IM to get the imaginary part. You can see that that's not really expanding anything. It just gives us back the real part. Since I do not want the e to the I deltas and such, I want to expand this to write out all of the actual real and imaginary parts, and then take the real part. And I'll do the same thing over here. And when I do that, oops, where did I? Oh, that's my problem. Can't have that there. When you do that, you get two equations, which is convenient because you have two unknowns from your original guess. You don't know what the amplitude is, and you don't know what that phase shift is. So we've got two equations for two unknowns, so we can solve that easily enough. We're just going to, again, we're going to cheat. We're going to do things the easy way and let Mathematica do the work for us. So we want to solve for A and delta. And it's these equations that I want to solve. So I'll plug those equations in to my solve function. When I do this, you will see why are you saying it's saying it's not a valid variable because it's assuming that this is a variable when I need to put this in a list, so I need the curly brackets. Easy fix. So you can see, I'm going to scrunch that down a little bit. You can see we've got two different solutions that, and you can see here these differ by an overall minus sign, and everything else is exactly the same. So I am going to, we'll just do a quick look at solution number 1. So I'm going to plug this one in. I'm going to plug this. I'm just going to plot this so you can see what it looks like. I'm going to plot this, and we're going to plot it. We're going to see what happens as we change the driving frequency. We'll go from 0 to, let's say, 3. And we'll make the plot range go to all, so we can see everything. And actually, that's it. We'll just keep the plot range to all. Now, if I run this, it's not going to give me anything because there's a bunch of variables in blue here, which I've got to define. I'm going to go ahead and do that. I'll just do it up here for convenience sake. We'll say you have a driving frequency of 1 Newton. The mass is 1 kilogram. The damping constant, we'll just put a little bit of damping in. Make that 0.1. And the we'll make the driving, we'll make the natural frequency, we'll make that 1.5. So this should give us a peak around 1.5. And you see we do get a peak around 1.5, but this has a negative sign in front, so everything's negative. So, we could continue going with this solution. It technically works, but we really want to use this other solution that's positive. So we are going to use solution number 2 that it spat out. And we're going to take a look at that instead. Actually, I'll leave this one here for reference. So this is going to be solution number 2. First things first. I'm gonna call this A2 since it's the second solution. And let's actually see what that looks like if we can simplify this a bit. I'm gonna go ahead and clear my kernel so that all of the variables I just defined, we're going to undefine those so I don't have to, we can keep it in variables and see what that looks like. You can see it's got a much simpler form. And then I can do the same thing for the delta, although I won't even do it for the delta. We're just going to keep it like this. Well, let's do it for the delta. It's nice to have simple things. Copy all of this. Now, you'll note that our phase shift here, it's got the arctangent function. It's also got this plus 2 pi times an integer. All it's really saying is that the arctan function is, or the tan function is periodic. So when you take the arctan, you're going to get the same result if you add 2 pi times an integer to your result. So that's just expressing the fact that it's periodic, but we're only going to be concerned with the period from 0 to 2 pi. So we can try to simplify this. I don't think it's going to simplify all that much. Well, it's actually a pretty decent improvement, but still pretty nasty. So we're going to go ahead and actually just plot these and try to make it look a little bit nicer. So what I'm going to do, let's see, how do I want to do this? We're going to do plot. We're going to do plot A2, comma, delta 2. And we'll go plot range goes from, and then we'll just say plot range is all. We're going to plot this from omega equals 0 to 3. Let's put some plot legends on so we know what's what. And the plot legend, the first thing I wrote down was the amplitude. So that'll be A. The second thing was the phase shift. So that'll be delta. And I still got a bunch of variables in blue, so I need to redefine those. So we'll copy that down here. We'll go like this. And you can see you've got your, you can see what happens to your phase shift and your amplitude. You can see, just like we had with the original case, if you're close to that resonance or that natural frequency, if your driving frequency is close to that resonance frequency, in this case, the natural frequency is about 1.5. If you're close to 1.5, you've got a big peak. Going from one side of the peak to the other, you actually shift phase. So you're going from a delta of pretty much 0, and then you jump up to just about pi. So you go 180 degrees out of phase as you pass resonance, which means your amplitude is either in phase or out of phase with the driving frequency. So the way to think about this is if your driving frequency is smaller than resonance, then you're in phase. So every time you push forward, you're pushing forward, the amplitude is going forward. If your driving frequency is too large, you're pushing too frequently, then you're 180 degrees out of phase. So every time you're pushing in the opposite direction of the amplitude. Just something to pay attention to as you're exploring the physics of this. I am going to go ahead and say we're going to stop this video here because I think it's getting a little long. We will continue to explore the physics in the next video. But please do click the like if you liked the video, and if you'd like to see more of these, please click subscribe.